Welcome to the AMD Versal AI Engines for DSP End-to-End Design Flow Quick Take video. In this video, we'll walk through how to create a Vivado extensible platform and an AI engine component in the AMD Vitis Unified IDE. Review source files, configure DSP library parameters using a CSV file, run compilation and simulation, analyze latency and throughput, explore the Vitis export to the AMD Vivado flow, and finally provide a demo video showing a seamless hardware-software integration. Let's begin. Click the Vivado Design Suite icon on the taskbar, then select Create Project. Click Next. Enter your project details and continue by clicking Next. Select the required project type and click Next. Add sources and constraints if needed. Choose the board for your project and click Next. Then review the summary and click Finish. Now, click the AMD Vitis tool icon on the taskbar to launch Vitis Unified IDE. When prompted, set your workspace. This is where your project files will be stored. Once selected, click Open to enter the IDE. Inside the IDE, go to File, New Component, AI Engine. In the dialog box, enter the component name, confirm the location, and click Next. In the Import Sources section, click Add Folders, then select the data and SRC directories. Ensure that all files are included. Click Next to select a hardware design. In this step, select Hardware Design and choose the required XSA. Review the summary and click Finish. Your AI engine component is now created and appears in the Vitis Components window, with a structured hierarchy for settings, sources, and outputs. Next, let's review the FIR filter graph. Expand AI Engine, Sources, SRC, and open FIR1_graph.h, which is an example source file. This file defines FIR and FFT filter parameters, coefficients, declarations, and kernel connections. Update the kernel connections as required for your design, then go to File, Save to store the changes. Now, download the Vitis library's zip file from GitHub and extract it into your project directory. The configuration parameters varies for different functions. This information can be found in the Vitis library's user guide. For example, the configuration parameters for the FFT window function is provided as shown here. Details like name of the parameter, type, default value, and its description are provided in the table. The Vitis library's user guide provides an extensive set of information on the configuration benchmark / quality of results QOR values for each of the functions as a configuration database. This section provides the L2 performance benchmarks and QOR for the AI Engine Digital Signal Processing DSP library elements with various configurations. The results are extracted from hardware emulation-based simulations. The configuration database provides an estimate of the latency, throughput, and the resource utilization, such as number of memory banks and AI engine tiles required for different combinations of various data types and coefficient types. Also, the configuration databases will have around 3,000 to 5,000 test results for an early estimation. These tables are also available in CSV format in the Vitis library's location as shown. Open the CSV in Excel or VS Code using an Excel Viewer extension. Use filters to narrow down parameters, for example, filter TP point size to choose precision values that best suit your design. Once finalized, use these values to validate or update the parameters in your FIR1_graph.h file. With all files updated, it's time to build and simulate the design. In the Flow window, ensure your component is selected and click Build under AIE Simulator / Hardware to compile it. Monitor the progress in the Output tab. Next, expand AI Engine. Settings and OpenLaunch.json. Select the AI Engine Simulator, confirm the target is set to AIE Simulator, then close the tab. Now click Run under AIE Simulator/hardware to start the simulation. Progress messages appear in the console and task windows. Once simulation completes, latency and throughput results are automatically generated. Open the default .run summary file using Vitis Analyzer, either from the command line or through the analysis view. In the Latency tab, you'll find first, last, and average latency metrics for each kernel or kernel-to-kernel connection. Switch to the I/O tab to view throughput estimates in megabytes per second. You can export this data as CSV for further analysis or visualization. Now, let's look at how Vitis and Vivado work together through the Vitis export flow. In many designs, hardware platforms are developed alongside AI engine graphs and PL kernels, often by different teams. The Vitis export flow enables smooth collaboration by allowing bidirectional handoffs between Vitis and Vivado, so updates can be shared easily at key stages. Using the V++ export archive command, all design data and metadata are packaged into a Vitis metadata archive VMA file, skipping Vivado synthesis and implementation. This archive allows both tools to stay in sync through multiple design iterations. Let's start with the platform creation flow. Inside Vitis, we compile the AI engine and HLS kernels, set up the system connections, and use the linker to generate a Vitis metadata archive, or VMA, which will later import back into Vivado. Next, we move back to Vivado tool and import the VMA file, which creates the Vitis region design. From here, we can refine the hardware, run implementation, and export a fixed XSA for embedded software development or hardware testing. This round-trip flow between Vivado and Vitis ensures smooth communication and a seamless hardware-software co-design experience, all within the Versal development ecosystem. In this demo, we'll walk you through the complete end-to-end flow of developing a Vitis subsystem, or VSS, and integrating it with a custom Vivado extensible platform, targeting the Versal VCK190 device. This demo uses a custom extensible Vivado design that integrates RTL, AI engine, and HLS modules through the Vitis flow. Firstly, unzip the Vitis tutorial zip file. After unzipping it, go to the required project location as shown. These are the design source files that we are working on in this demo video. Let's first set up the Vitis environment. Begin by sourcing the tool setup script using source Vitis installation path /setting 64.sh. If your design uses a pre-built Linux platform, set the SDK target sysroot variable to point to its installation path. Export SDK target sysroot equals install path. With the environment configured, we're ready to move into the Vitis export flow for seamless integration between Vitis and Vivado. Makefiles are provided to build the entire design directly from the lab's top folder. Running the build will automatically compile all required RTL, AIE, and HLS components, ensuring everything needed for the Vitis subsystem is ready during the linking process. We'll begin by preparing the VSS component. Enter Make VSS in the top-level folder. This involves adding AI engine, HLS, and RTL modules, and then verifying the AI engine functionality using both MATLAB VFS and Python VFS. This step ensures each subsystem is functionally validated before integration, giving us confidence in the design's behavior and performance. The build process generates the Vitis subsystem archive, VSS_top.vss, the AI engine library, libadf.a, and the HLS or RTL object files .xo, all ready for integration into the Vivado or Vitis platform design. Next, make Vivado_platform, where we'll prepare a custom flat, non-BDC platform. Here, we configure the essential building blocks, including the SIPs, AI engine, NOC, clocking, and AXI Smart Connect. Once configured, we export an extensible XSA, which serves as the handoff point for integration inside the Vitis tool. The Vivado tool build generates the project file vck190_thin_vivado /vck190_thin.xpr, the Vivado project directory with design and implementation data, and finally the hardware platform archive vck190_thin.xsa, the main output used for Vitis or Model Composer integration. After that, we'll switch to the Vitis tool. Enter make Vitis_IPVMA_export. In this stage, we'll integrate the VSS component along with additional HLS kernels using the Vitis linker. We'll also apply the new Vitis clocking enhancements designed specifically for HLS components, enabling better synchronization and performance control. Once the system is fully connected, we export the combined AI engine and PL subsystem as a VMA file. The Vitis export process generates the integrated hardware archive vck190_thin.vma located in Vitis/build hardware, which serves as the final design handoff for software development. Next, open the Vivado platform project from the Vivado folder using Vivado build /vck190_thin_vivado/vck190_thin.xpr. Then, open the top block design vck190_thin in IP Integrator. From the Tcl console, import the VMA archive using Vitis import_archive /Vitis/build hardware /vck190_thin.vma. This flow highlights the seamless communication between Vivado and Vitis. Vivado exports the XSA for system integration, and Vitis generates the VMA, which is imported back into Vivado for final implementation. Together, they enable a unified hardware-software co-design experience for Versal platforms. And that's the complete workflow, from building the subsystem to cross-tool integration, all working together to simplify and accelerate Versal solution development. This workflow demonstrates how Vitis and Vivado tools collaborate for Versal development. Starting with environment setup ensures tool compatibility. Automated builds simplify subsystem preparation and validation. Vivado provides the hardware platform, XSA, while Vitis integrates AI engine and PL components into a unified design, VMA. Finally, importing the VMA back into Vivado closes the loop, delivering a streamlined end-to-end design flow for Versal platforms. Thank you for watching.